So let me talk about congruence classes. We just defined congruence modulo and ideal. If you have a ring R and an ideal I in a ring R, then two elements A and B of the ring are called congruent modulo I if the difference A minus B is in I. That's the definition. If A and B are congruent modulo I, then you write A congruent to B modulo I. That's the notation. Okay? And we prove that it's this relation of congruence modulo I is an equivalence relation, meaning every element is congruent to itself. If A is congruent to B, then B is congruent to A. And if A is congruent to B and B is congruent to C, then A is congruent to C. This holds for all A, B, C. Now, because this is a equivalence relation, if you remember, it defines a partition of the ring R. So here's the ring R. Here's a cartoon of the ring R. A Venn diagram better be closed. If you give me an element, you have this relation, congruence modulo I on this set R. If you give me an element of the ring, I can collect all the guys who are related to A. And that's called an equivalence class. And then I can take another guy which is not in that class, maybe B, and look at all the guys that are related to B. That's called another equivalence class. And these classes form a partition of R. This is a general fact about equivalence relations, pretty much the only fact that we proved about equivalence relations. Okay, so let's headline this equivalence classes. And I'll say since congruence modulo I is an equivalence relation, on R, it defines a partition of R into what are called equivalence classes. And recall that equivalence class of an element A in R means the set of all elements that are related to A. The set of all elements of R that are related to A via this relation. So for example, this is a cartoon for that. In other words, the equivalence class of A consists of all B in R such that B is related to A. This set is going to be denoted by the notation A plus I. And this notation is a good notation because you need to, since you can verify, this notation sort of indicates what this set is. Verify that the guys that are related to A are simply these guys. A plus some element of I. Take A and add some element of I. That's a thing that's related to A, because if you subtract A from it, it's in I. And these are precisely all the things that are related to A. And what's a good notation for this set? Well, A plus I. Okay, so that's the equivalence class of A. I have a little more notation to go through regarding equivalence classes, except so maybe we'll go to a second page here. Or maybe we can fit it on this side. Oops. So continuing on, some more notation, more nomenclature, let's say. This is such a fundamental concept, there is quite a few words associated that you have to get used to. First, we say that A plus I, this set that we just defined, is the congruence class of A. Modulo I. It's also called the coset of A. Or the congruence class of A. Okay. Second, a subset of R is called a congruence class if it's one of these. A subset capital B of R is simply called a congruence class if B is the congruence class of some element for some B in R. Okay. And in this case, little b is called a representative for this congruence class. And we say little b is a representative for the class capital B. And I know this is a lot of new words, but when we do the example of Z mod NZ, which we have already studied in chapter 4 in great detail, in the next video, I think it will be much easier to parse all these definitions after that example. But I want you to notice simply that a congruence class can have many representatives. And this is a source of a lot of confusion, so just be aware of that. And finally, one more notation. It's not a new word, but a notation, the set of all congruence classes. The set of all congruence classes mod I is denoted by R mod I. And I'll remind you that because congruence modulo I is an equivalence relation, the set R is a disjoint union of all the distinct congruence classes. Remember that I is a disjoint union of all the distinct congruence classes. Okay, so let me just take stock of all the new words we have. We have quite a few. The setup is always you have a ring and an ideal, R and I. Two elements of the ring are called congruent modulo I if the difference is in I. This is an equivalence relation on the set R. So because it's an equivalence relation, it breaks up your R into pieces. One piece consists of all the things that are related among each other, and here is another piece of all the things that are related among each other, etc. Since this is an equivalence relation, it defines a partition of R into what are called equivalence classes. Equivalence class of an element means all the things that are related to A. And an equivalence class of an element A is denoted first of all by this notation A plus I down on the right side. And it consists of all things that look like A plus an element of the ideal I. And we say that A plus I, going to the left hand side of the page, we say that A plus I is the congruence class of A. A subset of the ring is called a congruence class, not of something, just a congruence class, if it's a congruence class of some element. So if it has that form, B plus I for some B. And the set of all congruence classes finally is denoted by R mod I. So that's the collection of all the new words we have. And since again this is an equivalence relation, this A mod B, A congruent to B mod I is an equivalence relation. The set R, sorry, I shouldn't have said I here, that's a typo. R is a disjoint union of the distinct congruence classes. So next we'll redo the example that we have seen before already, the example of Z mod N.